In the outer reaches of the solar system, beyond the orbit of Neptune where sunlight arrives as little more than a whisper, a dark object moves through space with the patience of geological time. Atlas carries within its nucleus the frozen memory of another star, materials that condensed in a stellar nursery so distant that its light has not yet reached Earth after travelling for millions of years. The comet's surface, blackened by cosmic radiation over eons of wandering, absorbs the faint warmth of the sun, a star that did not witness its birth, did not spin the disk of dust from which it formed. This wanderer measures perhaps a kilometre across, a city-sized fragment of interstellar ice and rock that has travelled for millions of years through the cold between stars. Its journey began in a solar system whose planets formed from different dust, whose chemistry bears the signature of stellar winds that never touched our world, whose heavy elements were forged in the heart of a red giant star that exhausted its fuel and died while our own sun was still a gathering cloud of hydrogen. Only now, as it falls inward toward the sun's gravitational embrace, does this ancient traveller begin to stir from its long sleep. The nucleus rotates slowly, perhaps once every few hours, tumbling end over end as it has done for countless millennia in the darkness between star systems. Each rotation reveals different patches of primordial ice water that froze when mammoths walked the Earth, carbon monoxide that condensed in temperatures colder than liquid nitrogen, methane that remembers the chemistry of worlds that never knew the touch of life. These substances lie locked within the comet's heart like fossils of another world's atmosphere, preserved in the ultimate freezer of interstellar space. Scientists studying its light signature find chemical markers that speak of stellar processes billions of years old, isotope ratios that whisper of nucleosynthesis in the heart of a star that died before our sun ignited its first nuclear flame. The deuterium to hydrogen ratio tells stories of cosmic ray bombardment during the long journey between stars. The carbon isotopes reveal the signature of stellar wind from an aging giant star, material blown into space when fusion could no longer support the star's outer layers against the pull of gravity. As 3I Atlas continues its inward fall, moving at 30 kilometers per second relative to the Sun, the solar wind begins its patient work of transformation. Charged particles streaming from the Sun at 400 kilometers per second, 1,000,000 times faster than Earth's swiftest winds encounter the comet's outer layers, beginning the slow alchemy that will soon paint the darkness with borrowed light. The process unfolds with the same inexorable rhythm that carved the Grand Canyon grain by grain, that lifted the Himalayas centimetre by centimetre. Only here, in the vastness between worlds, the sculpture is made of gas and dust, ephemeral as breath in winter air. The comet's trajectory, calculated with the precision that only gravity allows, carries it on a hyperbolic path that will never repeat in human memory or geological time. Unlike the familiar comets that return to our skies in predictable cycles, Halley's Comet every 76 years, Comet Hale-Bopp every 25 centuries, 3I Atlas follows a course that speaks of origins beyond the Sun's family. Its speed exceeds escape velocity by a comfortable margin. It moves too fast to be captured, too swift to become a permanent resident of our solar neighbourhood. This is a visit, not a homecoming, a brief encounter between strangers in the cosmic dark. The visitor's path carries it through regions of space that have witnessed the entire history of the solar system. It passes through zones where comets from the Oort cloud begin their million-year journeys toward the inner planets, where the sun's gravitational influence grows strong enough to bend the trajectories of wandering ice mountains. Here, in this realm of gravitational transitions, the boundary between what belongs to our star and what belongs to the galaxy blurs into mathematical abstractions that exist only in the minds of celestial mechanics. In observatories scattered across Earth's night side, from the high deserts of Chile to the volcanic peaks of Hawaii, astronomers track the visitor's approach with instruments sensitive enough to measure the whisper of starlight reflected from its surface. They find in its spectrum the chemical fingerprints of water older than the oldest rocks on Earth, carbon that condensed in the atmosphere of a red giant star whose planets, if they existed, were long ago consumed by their swelling sun. The nitrogen in 3I Atlas remembers the supernova explosions that seeded space with heavy elements, stellar deaths that occurred when the universe was young and galaxies were still learning how to spin. The comet carries within its frozen heart a library of stellar evolution, written in the language of atoms forged in nuclear fires that burned billions of years ago. Every molecule of water ice contains oxygen nuclei, created in the burning helium core of a massive star. Every grain of silicate dust holds silicon atoms forged when nuclear fusion converted neon into heavier elements in stellar furnaces hot enough to melt planets. This is matter that has travelled between the stars, carrying the chemical signature of stellar death and rebirth across distances that light takes millennia to cross. Yet mysteries linger in the data, questions that even the most precise measurements cannot answer with certainty. How long did this fragment of ice and rock wander in the darkness between stars before the sun's gravity drew it inward? Was it ejected from its birth system by the gravitational dance of giant planets? Or did the death of its parent star scatter it into the galactic void? What cataclysm or gentle gravitational nudge sent it on this journey across the spiral arm of the Milky Way? Through regions of space where the density of matter is so low that atoms are separated by distances larger than football fields. The comet itself holds these secrets locked in its nucleus. Stories that will only partially unfold as solar heating begins the process of sublimation in the weeks to come. The layers of ice that will soon boil away into space preserve a record of interstellar conditions that existed when woolly rhinoceros grazed in valleys that are now beneath city streets, when the last ice age locked vast quantities of Earth's water in continental glaciers. But the deeper layers, the core materials that formed in another stellar system, will likely remain frozen and hidden, carrying their secrets past Mars and back into the darkness beyond. The visitor approaches with the patience of cosmic time, its path as predictable as planetary motion, yet as unique as a fingerprint in the cosmic record. In a universe where most objects orbit in endless repetition, planets around stars, stars around galactic centers, galaxies in their slow gravitational waltz through expanding space, 3I Atlas traces a trajectory that speaks of beginnings and endings, of journeys that span the spaces between stars and connect the chemistry of distant worlds. Soon, very soon in astronomical terms, it will begin to shed its ancient ice into the solar wind, painting a temporary brushstroke of light across the darkness. This signature will be written in the language of sublimation and solar pressure, visible for a brief moment against the eternal backdrop of space. A message from another star system delivered across the vast loneliness of interstellar distance. Beyond the orbit of Neptune, where the sun appears as little more than the brightest star in a field of distant lights, the first whispers of transformation begin to stir within the ancient nucleus of 3I Atlas. Here, in the realm where temperatures hover near absolute zero, and matter exists in states unknown on any terrestrial world, the visitor from another star system starts its slow awakening from the deep freeze of interstellar space. The process begins with the most volatile substances locked within the comet's heart carbon monoxide ice, that forms at temperatures so low they would instantly freeze human breath into crystals harder than steel. As the sun's radiation penetrates the darkened surface layers, molecules that have remained motionless for millions of years begin their first tentative vibrations. The energy required to break these ancient molecular bonds arrives at the speed of light, but accumulates with the patience of geology, photon by photon, warming material that condensed when the universe was younger, and the local group of galaxies was still settling into its current configuration. Scientists monitoring the comet's approach detect the earliest signs of this awakening in the subtle changes of reflected sunlight. Spectroscopic analysis reveals the faint signature of sublimation, the direct transition from solid to gas that bypasses the liquid phase entirely in the vacuum of space. Carbon monoxide molecules, freed from their crystalline prison after eons of stillness, escape into space at velocities measured in hundreds of meters per second. These first fugitive gases carry with them the chemical memory of another star's planetary disk, isotope ratios that speak of nuclear processes that occurred in stellar cores long before our solar system condensed from its own primordial nebula. The liberated gas molecules immediately encounter the solar wind, that constant stream of charged particles flowing outward from the Sun at supersonic speeds. Here, 4 billion kilometers from the solar surface, the wind has thinned to a whisper of its former intensity, yet it still possesses enough energy to ionize the escaping gases and bend their trajectories according to the invisible architecture of magnetic field lines. The interaction creates the first faint glow around 3E Atlas, a barely detectable halo of luminescence that astronomers call a coma, the ghostly atmosphere of a world that has no permanent air. This embryonic coma expands with dreamlike slowness, gas molecules drifting outward from the nucleus at walking speed relative to the comet's center of mass. The process follows laws of physics that govern everything from the evaporation of morning dew to the stellar winds of red giant stars, the same principles of thermodynamics and fluid mechanics that drive weather systems on Earth and atmospheric escape on Mars. Yet here, in the near vacuum between worlds, these familiar processes create structures of ethereal beauty, geometries of gas and dust that exist only in the realm between planets. The comet's rotation, that slow tumble acquired during its journey between star systems, creates subtle variations in the rate of sublimation across its surface. Areas that face the Sun directly lose their volatile ices faster than regions in perpetual shadow, creating jets and fountains of gas that follow the ancient rhythm of the nucleus's spin. These jets carve temporary channels in the thin atmosphere surrounding the comet, spiral patterns that trace the gravitational and rotational forces acting on material older than any mountain range on Earth. As the escaping gases expand into space, they carry with them microscopic particles of dust, silicate grains and organic compounds that formed in the disk of another star, matter that witnessed the birth of worlds we will never see. These dust motes, each no larger than particles of cigarette smoke, become visible when sunlight strikes them at the proper angle. They scatter photons with the same efficiency that makes Earth's sky blue, creating the optical phenomenon that transforms a dark chunk of ice into a celestial beacon, visible across interplanetary distances. The temperature of the nucleus surface rises by degrees so small they would be imperceptible to human senses, yet each fraction of a Kelvin represents a fundamental change in the comet's state of being. At -200 degrees Celsius, carbon monoxide ice begins its transition to vapor. At -180 degrees, nitrogen ice joins the exodus. The comet sheds these ancient atmospheres layer by layer, revealing progressively deeper strata of material that froze under different stellar winds, in the gravity well of a star whose light will never reach our telescopes. Observatories on Earth record these changes with instruments sensitive enough to detect the absorption lines of individual molecular species in the comet's growing coma. Each spectral signature tells part of the story, water vapor from ice, that remembers the chemistry of primordial oceans that never formed, methane from hydrocarbons that condensed in stellar winds rich with carbon expelled from the burning cores of aging giants. The data streams from these observations reveal not just the composition of 3I Atlas, but glimpses of the stellar nursery where it was born, the physical conditions that existed in another solar system billions of years ago. Yet the comet's awakening proceeds with maddening slowness from a human perspective, each day bringing changes measured in parts per million rather than dramatic visible transformations. The coma expands at roughly the speed of a gentle breeze, growing from a few hundred kilometers across to perhaps 1,000 over the course of weeks. This temporal rhythm reflects the vast scales of astronomical processes, where significant events unfold over periods longer than human civilizations but shorter than the erosion of mountain ranges. The mystery of Three-Eye Atlas deepens as more of its chemical signature becomes visible to Earth-based instruments. The ratios of different isotopes suggest a formation environment unlike anything in our local stellar neighborhood, possibly indicating birth in a region of the galaxy where different generations of stellar death and rebirth have enriched space with unusual combinations of heavy elements. The comet becomes a messenger not just from another star system, but potentially from a different epoch of galactic evolution, when the chemistry of star formation followed slightly different rules than those that govern the condensation of our own sun and planets. The visitor continues its patient fall toward the inner solar system, now wearing a gossamer atmosphere that makes it visible to the most sensitive telescopes on Earth. This first awakening represents only the beginning of a transformation that will unfold over the coming months, as Three-Eye Atlas sheds the accumulated ice of interstellar wandering and reveals the ancient secrets locked within its core. The process follows the same inexorable logic that governs all phase transitions in the universe, from the sublimation of dry ice in terrestrial laboratories to the stellar winds that strip atmospheres from planets orbiting too close to their parent stars, in the depths of space where matter and energy exist in states of exquisite balance. The comet from another star begins to paint its temporary signature across the darkness, molecule by molecule, grain by grain, with the patient artistry of physical law applied across the vast canvas of interplanetary space. In the void between Neptune and Jupiter, where space seems empty but contains more history than any library on Earth, two different winds meet for the first time in the memory of the galaxy. The solar wind, that constant exhalation of charged particles from our star's corona, encounters matter that remembers the breath of a different sun, material that carries within its atomic structure the signature of nuclear fusion that occurred in stellar cores light years away and eons ago. The solar wind at this distance moves with diminished intensity compared to its fury in the inner solar system, yet it still races outward at velocities that dwarf the fastest storms on Earth. Protons and electrons, stripped from hydrogen atoms in the sun's million-degree corona, stream past the awakening comet at 400 kilometers per second, carrying with them the magnetic fingerprint of our star's rotating field lines. These particles have travelled for weeks to reach this distant realm, expanding and cooling as they flow through the increasing volume of space, yet they retain enough energy to fundamentally alter any matter they encounter. The gases escaping from Three-Eye Atlas: carbon monoxide, nitrogen, traces of water vapour older than the oldest fossils meet this solar wind with the inevitability of collision between different epochs of cosmic history. Each molecule of comet gas, liberated after millions of years of frozen stillness, suddenly encounters radiation and charged particles that originated in nuclear reactions occurring at 15 million degrees Celsius. The contrast embodies the vast temperature range of the universe, from the near absolute zero of interstellar space to the thermonuclear furnace at the heart of stars. When solar wind protons collide with molecules escaping from the comet's nucleus, they strip away electrons with the efficiency of cosmic chemistry, ionizing neutral gases and transforming them into a glowing plasma that responds to magnetic forces. Carbon monoxide becomes carbon monoxide ions, their electrical charge making them visible to instruments that detect the electromagnetic spectrum across wavelengths from radio to ultraviolet. This ionization process releases photons at specific frequencies, creating spectral lines that astronomers can identify with the precision of fingerprinting, each emission signature corresponding to a known atomic or molecular transition. The interaction creates phenomena that exist nowhere else in the solar system with quite the same character. The comet's growing coma becomes a laboratory for plasma physics, where gases from another stellar environment undergo transformation by the radiation pressure and magnetic fields of our own star. Sodium atoms, freed from dust grains that condensed in the atmosphere of a red giant star, glow with the same yellow wavelength that colours streetlights, creating a faint aureole around the comet's nucleus that telescopes can detect across billions of kilometers of space. Solar ultraviolet radiation, invisible to human eyes, but capable of breaking molecular bonds with surgical precision, dissociates complex organic compounds that survive the journey between star systems. Methane molecules split into hydrogen and carbon radicals. Water vapor separates into hydrogen and hydroxyl groups, each fragmentation releasing stored chemical energy that has remained locked in molecular bonds since the comet's formation. These photodissociation products create their own spectral signatures, painting rainbow colours across instruments designed to decode the chemistry of distant worlds. The magnetic field lines carried by the solar wind begin to drape around the expanding coma like invisible silk, creating a magnetosphere in miniature around the visitor from interstellar space. This magnetic cocoon deflects some of the incoming solar wind, while allowing other particles to penetrate deeper toward the nucleus, establishing circulation patterns in the comet's thin atmosphere that follow the same principles governing weather systems on planets, but operate on scales and timescales utterly foreign to terrestrial experience. As the coma continues to expand, now reaching diameters comparable to small planets, it develops internal structure that reflects the complex interplay between solar radiation pressure and the comet's own gravitational field. Heavier molecules, those containing carbon and nitrogen and oxygen atoms forged in the nuclear furnaces of massive stars, fall back toward the nucleus under their own weight, while lighter hydrogen atoms escape to space at velocities approaching several kilometers per second. This gravitational sorting creates atmospheric layers as distinct as those in Earth's stratosphere. Though composed of materials and existing under conditions that make terrestrial analogies seem quaint, the dust grains carried along with the escaping gases begin their own transformation under solar influence. Ultraviolet photons heat these microscopic particles to temperatures that would glow red hot if they existed in sufficient density, causing them to radiate thermal energy at infrared wavelengths that Earth-based telescopes can detect and analyze. The thermal signature reveals the composition and size distribution of dust that formed in another stellar system, providing clues about the physical processes that governed planet formation around a star we will never see. Observatories monitoring the comet's evolution detect subtle changes in the polarization of scattered sunlight, indicating that the dust grains possess preferred orientations imposed by the interaction between solar radiation pressure and the comet's weak gravitational field. This alignment creates optical effects similar to those that make Earth's sky blue and sunsets red, but operating under physical conditions so extreme that the familiar becomes alien. The understood becomes mysterious. The chemical signatures emerging from the coma reveal isotopic ratios that challenge assumptions about stellar nuclear synthesis in distant regions of the galaxy. The deuterium content of water vapor suggests formation in an environment where cosmic ray bombardment occurred at rates different from those in our local stellar neighborhood. The carbon-13 to carbon-12 ratio indicates processing through stellar wind mechanisms that operated under physical conditions, unlike those that enrich the molecular cloud from which our solar system condensed. Scientists studying these interactions realize they are witnessing a unique experiment in comparative stellar chemistry. As materials that recorded the nuclear history of one star undergo transformation by the radiation and particle flux of another, the comet becomes a laboratory for astrophysics, where theories about stellar evolution and galactic chemical evolution can be tested against direct observation of matter that has travelled between different stellar environments. The solar wind continues its patient work of ionization and dissociation, gradually stripping away the outer layers of ice that accumulated during the comet's interstellar journey. Each layer reveals slightly different chemical compositions, like tree rings that record not seasonal changes, but the varying conditions of interstellar space encountered during a journey that spanned millions of years and hundreds of light-years of galactic distance. Yet the fundamental mystery of 3I Atlas deepens rather than resolves as more data accumulates. The comet's response to solar heating follows patterns that suggest internal structure unlike any object previously studied, with volatile materials distributed through the nucleus in ways that speak of formation processes or evolutionary history that remain beyond the reach of current theoretical understanding. In the growing theatre of space around 3I Atlas, where solar radiation pressure begins to assert dominance over the comet's feeble gravity. The first visible brushstrokes of the tail begin to emerge against the stellar backdrop. This phenomenon unfolds with the same inexorable logic that governs the formation of river deltas and the erosion of coastlines. Yet here the medium is not water and sediment, but ionized gas and microscopic dust grains, sculpted by forces that operate across scales from atomic to planetary. The tail materializes not as a single coherent structure, but as two distinct phenomena that follow different physical laws and respond to different aspects of solar influence. The gas tail, composed primarily of ionized carbon monoxide and water vapor, aligns itself with the magnetic field lines embedded in the solar wind, creating a stream of glowing plasma that points directly away from the sun regardless of the comet's direction of motion. This magnetic choreography follows principles discovered in terrestrial laboratories, but operates here on a scale that dwarfs the largest particle accelerators, stretching across millions of kilometers of space with a geometric precision that only fundamental forces can achieve. The dust tail follows a different trajectory entirely, shaped by the gentle but persistent pressure of solar photons striking particles no larger than smoke from a wood fire. Each grain of silicate and organic matter, liberated from ice that froze when the Crab Nebula was still an ordinary star, experiences a tiny but continuous push away from the sun. The magnitude of this radiation pressure depends on the size and composition of individual particles, creating a separation effect that sorts the comet's debris by physical properties with the patience of geological processes and the precision of laboratory measurements. These microscopic architects of the comet's tail carry within their crystalline structure the chemical signature of stellar nucleosynthesis that occurred in another region of the galaxy. Silicon atoms forged in the carbon-burning cores of massive stars, iron nuclei created during supernova explosions that briefly outshone entire galaxies, magnesium ions that condensed from stellar wind enriched by the deaths of red giant stars. All of this stellar archaeology becomes visible as sunlight scatters from surfaces smaller than bacteria, yet carrying the accumulated wisdom of cosmic evolution. The spectroscopic analysis of light reflected from these dust grains reveals absorption features that correspond to mineral compositions unknown in meteorites that fall to Earth. The crystalline structure suggests formation temperatures and pressures that indicate condensation in an environment where stellar winds carry different proportions of heavy elements, where the chemistry of planetary formation followed pathways that produced compositions foreign to our local stellar neighborhood. Each photon of scattered sunlight becomes a messenger carrying information about physical processes that occurred around a star whose planets, if they existed, experienced geological evolution under the influence of different stellar radiation and different abundances of radioactive elements. As the tail continues to develop, growing longer with each passing day as more material escapes the comet's nucleus, it begins to exhibit internal structure that reflects the complex fluid dynamics of rarefied plasma interacting with magnetic fields. Streamers and filaments appear within the gas tail, following field lines that twist and reconnect according to hydrodynamic principles that govern phenomena ranging from solar flares to the behavior of fusion reactors. These structures form and dissolve over periods of hours or days, creating temporary geometries of a luminous gas that exist briefly against the permanent backdrop of stellar space. The dust tail, moving more slowly and following a gentler curve that traces the comet's orbital path, develops its own subtle architecture as particles of different sizes separate according to their response to radiation pressure. Larger grains, those approaching the size of sand particles, lag behind in the comet's orbit, while smaller fragments race ahead, creating a gradient of particle sizes that becomes visible through careful photometric analysis of scattered sunlight. This gravitational and radiative sorting creates a natural laboratory for studying the size distribution of interstellar dust, providing insights into the physical processes that governed grain formation in the disk of an alien star. Observers on Earth notice that the tail's brightness varies with a periodicity that matches the comet's rotation, indicating that the nucleus expels material preferentially from specific regions that face the Sun during each rotation cycle. This non-uniform outgassing creates jets of gas and dust that sweep through space like lighthouse beams, painting spiral patterns in the coma and tail that preserve the memory of the nucleus's tumbling motion. The spiral structure, barely visible even in the most sensitive telescopic images, follows mathematical relationships that describe fluid flow in rotating systems, from tropical cyclones on Earth to the spiral arms of galaxies. The chemistry visible in the tail's spectrum continues to reveal surprises that challenge theoretical models of comet composition and interstellar chemistry. Organic compounds appear that suggest formation in environments rich with carbon, expelled from asymptotic giant branch stars. Stellar atmospheres where carbon-to-oxygen ratios favour the production of complex hydrocarbons over the oxygen-rich silicates that dominate our solar system's rocky planets. These organic signatures hint at prebiotic chemistry that evolved under different stellar conditions, following reaction pathways that operated in molecular clouds enriched by different episodes of stellar death and rebirth. The tail's interaction with the interplanetary medium creates phenomena that exist at the intersection of plasma physics and celestial mechanics. Magnetic reconnection events, similar to those that trigger aurora on Earth and solar flares on the Sun, occasionally cause portions of the gas tail to disconnect entirely and drift away from the comet as independent plasma clouds. These disconnection events follow the same physical principles that govern magnetic storms in planetary magnetospheres, but operate here in the near vacuum of space, where particle densities are lower than the best laboratory vacuums, yet magnetic field strengths rival those in the cores of neutron stars. Earth-based observers tracking the tail's development notice that its brightness peaks not at visible wavelengths, but in the ultraviolet and infrared portions of the electromagnetic spectrum, regions where fluorescence from ionized gases and thermal emission from heated dust create the strongest signals. This spectral distribution reflects the fundamental quantum mechanical processes that govern light emission from atoms and molecules, the same transitions that create neon signs and laser light, but operating here under conditions of temperature and density that exist nowhere in human experience. The growing tail becomes a beacon visible across interplanetary distances, yet paradoxically composed of material so tenuous that its total mass would not fill a large building on Earth. This contradiction between visibility and substance reflects the vast scales of astronomical phenomena, where structures larger than planets can be composed of matter thinner than any earthly atmosphere, where light years of space can be bridged by phenomena that exist at the threshold of detectability. As 3 Atlas continues its approach toward the inner solar system, the tail that now streams behind it carries away forever some of the materials that recorded the chemistry and physical conditions of another stellar environment. Each gram of ice that sublimates, each dust grain that joins the expanding tail, represents the permanent loss of information about the comet's origin and history. The visitor from interstellar space gradually transforms itself from a repository of alien stellar chemistry into an active participant in our solar system's dynamics, its ancient ice becoming part of the solar wind that will eventually carry these molecules to the boundaries of heliospheric space and beyond. In the vastness between Mars and Jupiter, where the asteroid belt holds the scattered remnants of planetary formation in gravitational suspension, the influence of Jupiter begins to whisper across space to the approaching visitor from another star. This gravitational conversation operates at the speed of causality itself. Following the curvature of space-time that Einstein revealed governs the architecture of the universe, Jupiter, with its mass 2.5 times greater than all other planets combined, creates distortions in the fabric of space that propagate outward like ripples in a cosmic pond, reaching across hundreds of millions of kilometers to gently adjust the trajectory of 3I Atlas. The mathematics describing this interaction reduce to equations that would fit comfortably on a single page, yet they encode forces capable of flinging comets into the outer darkness, or drawing them into collision courses with the Sun. Jupiter's gravitational field, weakened by distance but never entirely negligible, exerts a force on the comet measured in newtons so small they would barely register on the most sensitive laboratory scales. Yet sustained over months and applied across the vast distances of interplanetary space, this whisper of attraction accumulates into trajectory changes measurable in kilometers, alterations that will determine whether 3i Atlas approaches Mars closely enough for detailed observation, or passes at distances that render it merely another point of light moving against the stellar background. The comet's path bends with the mathematical precision that governs all orbital mechanics, following curves described by solutions to differential equations that have remained unchanged since Newton first glimpsed their elegant structure. These equations make no distinction between comets born in our solar system and visitors from interstellar space gravity, operates according to principles that transcend stellar boundaries, applying the same physical laws that governed the formation of galaxies to the motion of objects no larger than city blocks. The democracy of gravitational influence ensures that 3i Atlas, despite its alien origin, must obey the same celestial mechanics that dictate the positions of Jupiter's moons and the timing of planetary alignments. As the comet falls deeper into Jupiter's gravitational well, though still millions of kilometers from the giant planet's cloud tops, subtle changes begin to appear in its orbital elements. Those 6 numbers that completely specify the size, shape, and orientation of its trajectory through space. The semi-major axis shifts by fractions of an astronomical unit. The eccentricity changes by decimal places invisible to casual observation, but measurable by the precision instruments that track objects across interplanetary distances. These modifications accumulate like compound interest, small changes that multiply over time to produce significant alterations in the comet's ultimate destination. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto add their own gravitational signatures to the complex dynamical environment surrounding the gas giant. These worlds, each comparable in size to Earth's moon or the planet Mercury, create perturbations within perturbations, gravitational harmonics that influence the precise details of how Jupiter's field affects the approaching comet. The mathematics describing these multi-body interactions require computational methods that push the boundaries of numerical analysis, calculations that must account for the positions and velocities of multiple objects moving in 3-dimensional space under the influence of forces that operate across scales from meters to astronomical units. The Great Red Spot, that persistent storm larger than Earth that has raged in Jupiter's atmosphere for centuries, serves as a visual reminder of the immense energies contained within the giant planet's roiling interior. The heat generated by Jupiter's continued gravitational contraction, the slow collapse that began when the planet formed from the solar nebula 4.5 billion years ago, drives atmospheric dynamics that create wind speeds exceeding those of the most violent terrestrial hurricanes. This internal energy source makes Jupiter a miniature star that never quite achieved the mass necessary to ignite nuclear fusion, a failed sun whose gravitational influence nonetheless shapes the architecture of the outer solar system. The comet's interaction with Jupiter's magnetosphere, that vast bubble of charged particles trapped by the planet's magnetic field, begins while 3i Atlas remains far beyond the orbit of Callisto. Jupiter's magnetic field, generated by convection currents in the planet's liquid metallic hydrogen core, extends across volumes of space that could contain multiple Earths. As the comet's expanding coma encounters the outer boundaries of this magnetosphere, the ionized gases in its tail experience forces that add subtle complexities to their trajectories, creating perturbations that become visible to instruments designed to study plasma physics in space environments. The gravitational dance between Jupiter and 3i Atlas unfolds with temporal rhythms that reflect the vast scales of astronomical phenomena. Changes in the comet's trajectory that require months to become apparent occur according to physical laws that operate instantaneously, yet their cumulative effects emerge only through the patient accumulation of small influences over extended periods. This temporal paradox, immediate cause producing delayed effect, characterizes much of celestial mechanics. Where the precision of mathematical prediction coexists with evolutionary processes that unfold over timescales longer than human memory. Astronomers monitoring the comet's approach use Jupiter's gravitational influence as a natural tool for trajectory analysis, employing the same techniques that spacecraft navigators use to plan missions to the outer planets. The subtle changes in 3I Atlas's orbital elements provide information about both the comet's mass and its internal structure. Since objects with different mass distributions respond differently to external gravitational forces, these measurements reveal that the visitor possesses a density suggesting a composition dominated by water ice, mixed with rocky material, consistent with formation in the outer regions of a stellar system, where temperatures remained below the freezing point of water throughout most of the planet-forming epoch. The precision required to track these gravitational interactions pushes ground-based telescopes to their operational limits, demanding measurements of angular position accurate to fractions of an arc-second angles, so small they correspond to the apparent size of a coin viewed from hundreds of kilometers away. Radio telescopes contribute their own observations, using radar techniques to measure the comet's distance and radial velocity with uncertainties measured in centimeters per second. These complementary observations create a dataset that constrains the comet's orbit with precision sufficient to predict its position years into the future, assuming no unexpected outgassing events or fragmentations alter its trajectory. The gravitational slingshot effect, that elegant transfer of orbital energy that spacecraft designers use to accelerate probes toward the outer planets, operates on 3I Atlas with characteristic astronomical subtlety. Jupiter's motion around the Sun creates a moving gravitational field that can either accelerate or decelerate objects that pass through its influence, depending on the geometry of their approach. The comet, approaching from the direction of interstellar space with velocity components that differ from those of solar system objects, experiences gravitational forces that modify not only its speed relative to Jupiter, but also its velocity relative to the Sun and its ultimate trajectory through the inner solar system. As 3I Atlas continues its approach, now visibly modified by Jupiter's gravitational embrace, it carries within its nucleus the unchanged chemistry of another stellar system, while following orbital mechanics that reflect the gravitational architecture of our own. This synthesis of alien composition and familiar dynamics creates a unique opportunity to study materials formed under different stellar conditions, while they follow trajectories governed by the same physical laws that regulate the motion of planets and the circulation of ocean currents on Earth. Between the orbits of Mars and Jupiter, where the debris of planetary formation drifts in gravitational exile, 3I Atlas enters the asteroid belt with the patience of geological time. This region of space, imagined by popular culture as a dense minefield of tumbling rocks, reveals itself in reality as a realm of profound emptiness, punctuated by isolated fragments that carry within their battered surfaces the memory of the solar system's violent youth. The largest asteroids, worlds like Ceres and Vesta that nearly achieved planetary status before Jupiter's gravity stirred the region into perpetual chaos, orbit in stately solitude separated by distances that spacecraft can cross for months without encountering anything larger than dust motes. The visitor from interstellar space moves through this sparse debris field like a ghost passing through a museum of cosmic history. Each asteroid it encounters, though separated by millions of kilometers of vacuum, tells a story written in cratered stone and metal, a narrative of impacts and near collisions that began when the Sun was young and has continued for 4.5 billion years. These fragments preserve in their mineralogy the chemical signature of the solar nebula, the disk of gas and dust from which all planetary bodies condensed during the epoch when nuclear fusion first ignited in the proto-sun's core. Vesta, that ancient protoplanet whose southern hemisphere bears a crater so large it nearly shattered the entire world, passes within a few million kilometers of the comet's trajectory. The asteroid's surface, mapped in exquisite detail by visiting spacecraft, reveals basaltic flows that solidified when Earth was still molten, when the bombardment of the inner solar system rained debris larger than mountains onto planetary surfaces that had not yet cooled sufficiently to support oceans or atmospheres. Vesta's differentiated interior metal core, rocky mantle, Basaltic crust demonstrates that this fragment once possessed sufficient internal heat to drive the same geological processes that shaped the terrestrial planets. Yet its small size doomed it to rapid cooling and geological death. The spectroscopic signature of Vesta's surface, dominated by pyroxene and plagioclase feldspar minerals that crystallized from molten rock, contrasts sharply with the chemistry emerging from 3I Atlas as its ancient ices continue their sublimation into space. Where the asteroid's spectrum reveals the products of high-temperature igneous processes, silicate minerals that formed in magma chambers heated by radioactive decay and gravitational compression. The comet's outgassing displays the signature of materials that condense directly from stellar wind at temperatures near absolute zero. These two objects, now sharing the same region of space, represent opposite extremes of planetary formation, one born in fire and molten metal, the other assembled from ice and organic compounds in the frozen outer reaches of a stellar system. Ceres, the largest object in the asteroid belt and the only one massive enough to achieve hydrostatic equilibrium and qualify as a dwarf planet, presents an even more intriguing comparison with the interstellar visitor. Recent observations have revealed that Ceres possesses a subsurface ocean beneath its rocky crust, liquid water that has remained unfrozen for billions of years due to heat generated by radioactive decay and tidal flexing. This hidden ocean, more voluminous than all of Earth's surface waters combined, may represent one of the most promising environments for life in the outer solar system. A biological laboratory that has operated in darkness and isolation since the epoch when complex multicellular organisms first appeared on Earth. The water ice that comprises a significant fraction of 3I Atlas carries isotopic signatures that differ subtly but measurably from the water locked within Ceres and other asteroid belt objects. The deuterium to hydrogen ratio in the comet's sublimating ice reflects the physical conditions that existed in another stellar system during the epoch of planetary formation, providing a comparative sample of primordial water that condensed under different stellar radiation conditions and cosmic ray bombardment rates. These isotopic differences, measured in parts per thousand, encode information about stellar nucleosynthesis and galactic chemical evolution that spans millions of years and hundreds of light-years of space. As 3D Atlas continues its traverse through the asteroid belt, its growing coma and tail interact with a tenuous dust environment that permeates this region of space. Microscopic particles, ejected from asteroid surfaces by micrometeorite impacts and solar wind sputtering, create an interplanetary medium so rarefied that its density falls far below the best laboratory vacuums, yet sufficiently populated to affect the propagation of the comet's outgassing through subtle collisional processes. The collision cross-sections involved in these interactions operate on scales measured in square nanometers, yet accumulated over millions of cubic kilometers of space, they create detectable modifications in the comet's spectroscopic signature. The asteroid Psyche, that metallic world composed primarily of iron and nickel that may represent the exposed core of a disrupted protoplanet, reflects sunlight with the distinctive spectral characteristics of metallic surfaces polished by eons of micrometeorite bombardment. The asteroid's composition, revealed through radar observations that penetrate its surface layers, suggests that this object once resided within the interior of a much larger body that possessed sufficient mass to undergo complete differentiation into core, mantle, and crust before some catastrophic collision stripped away its rocky exterior. Psyche now orbits as a naked planetary core, its metallic surface providing a window into processes that normally remain hidden beneath thousands of kilometers of rock. The gravitational perturbations caused by these asteroid encounters, though individually negligible, accumulate over the months-long traverse through the belt to produce measurable changes in 3I Atlas's trajectory. Each close approach, defined in asteroid belt terms as passage within several million kilometers, adds its small contribution to the comet's evolving orbital elements. The mathematical description of these multi-body interactions requires numerical integration techniques that account for the positions and masses of hundreds of significant asteroids, creating computational challenges that push the boundaries of celestial mechanics modeling. Trojans, Those asteroids that share Jupiter's orbit by residing at the gravitationally stable Lagrange point 60 degrees ahead of and behind the giant planet, create their own subtle influences on objects passing through their orbital resonances, these gravitational sweet spots, where the combined influence of Jupiter and the Sun creates stable equilibrium positions, trap not only asteroids but also dust particles and occasionally cometary debris, creating reservoirs of material that date to the solar system's formation epoch. The Trojan asteroids serve as fossils of the planet formation process, preserved in gravitational amber at locations where Jupiter's migration through the outer solar system deposited them billions of years ago. The comparison between 3I Atlas and the asteroid belt objects it now moves among reveals fundamental differences in formation environments and evolutionary histories. Where the asteroids bear the scars of 4.5 billion years of collisional evolution within our solar system's gravitational architecture, the comet carries materials that remained pristine during millions of years of interstellar travel, preserved in the ultimate deep freeze of space between stars. The chemical signatures emerging from the comet's nucleus provide a control sample for comparative planetary science, revealing how stellar chemistry and planetary formation processes operated under different initial conditions in another stellar system. Radio telescopes tracking the comet's progress through the asteroid belt detect subtle changes in the polarization and intensity of radar echoes reflected from its nucleus, suggesting that the sustained heating from solar radiation has begun to alter the physical structure of its surface layers. The same solar energy that drives the spectacular outgassing creating the comet's tail also works more subtly to modify the thermal and mechanical properties of materials that have remained unchanged since their formation around another star, beginning a transformation that will continue as long as 3I Atlas remains within the influence of our Sun's radiant energy. Across the diminishing gulf of space that separates 3I Atlas from the fourth planet, Mars grows from a ruddy point of light into a discernible disk that reveals the geography of an ancient world. The comet's approach toward Mars unfolds with the mathematical precision that governs all celestial encounters, yet each day brings subtle changes in the red planet's appearance as viewed from the visitor's perspective, transformations that reflect both the comet's motion through space and the slow rotation of Mars beneath its thin carbon dioxide atmosphere. The planet's distinctive rust-coloured hue, visible even through small telescopes on Earth, emerges from iron oxides that coat much of its surface, the chemical signature of water that once flowed in rivers and pooled in lakes across landscapes that now lie desiccated under skies too thin to support liquid water at most elevations. This oxidized iron, spread across continents larger than Earth's land masses, preserves in its crystalline structure the memory of an epoch when Mars possessed a thicker atmosphere and more temperate climate, when the greenhouse effect of carbon dioxide and water vapor created surface conditions that might have supported the chemistry of life. As Mars expands in the comet's view, the planet's topographical extremes become apparent through the play of sunlight and shadow across its rotating surface. Olympus Mons, that volcanic mountain 3 times taller than Everest, and broad enough to span the distance from London to Paris, casts shadows that creep across the Tharsis Plateau with the patient rhythm of planetary rotation. This extinct volcano, built by eruptions that continued sporadically for billions of years, represents the accumulated result of hotspot volcanism operating on a world without plate tectonics, where rising mantle plumes could build single volcanic edifices to heights impossible on more geologically active planets. The Great Canyon system of Valles Marineris, stretching across nearly a quarter of Mars's circumference, reveals itself as a scar that makes Earth's Grand Canyon appear modest by comparison. This vast rift system, carved by tectonic forces that split the planet's crust during its geological youth, extends deeper than the height of Mount Everest and could swallow the entire Mediterranean Sea with room to spare. The canyon walls expose geological strata that record billions of years of Martian history, layers of volcanic rock, impact breccia, and sedimentary deposits that chronicle epochs when the planet's climate and geological activity differ dramatically from present conditions. The polar ice caps, visible as brilliant white patches that wax and wane with Mars's seasons, consist primarily of frozen carbon dioxide with underlying deposits of water ice that may contain more H2O than exists in all of Earth's surface fresh water. These polar reservoirs represent the remnants of ancient Martian atmospheres, carbon dioxide and water vapour that condensed during periods of climate change and now lie locked in permanent cold storage at temperatures that would instantly freeze human breath. The seasonal sublimation and condensation of carbon dioxide at the polar caps drives atmospheric pressure changes that create planet-wide dust storms and modify the dynamics of the thin Martian atmosphere. Spectroscopic analysis of sunlight reflected from Mars's surface reveals mineral compositions that tell stories of aqueous alteration, chemical processes that required liquid water to operate over extended periods, clay minerals detected from orbit and confirmed by surface rovers, indicate environments where water remains stable long enough for complex weathering reactions to alter basaltic bedrock into hydrated silicates. These clay deposits, concentrated in geological formations that date to Mars's earliest epochs, suggest that the planet once possessed not merely transient water, but stable aqueous environments that persisted for millions or perhaps hundreds of millions of years. The two small moons of Mars, Phobos and Deimos, orbit their parent planet with periods measured in hours, rather than the weeks or months characteristic of larger planetary satellites. These irregularly shaped objects, each no larger than a city and bearing the heavily cratered surfaces typical of captured asteroids, race around Mars at altitudes so low that Phobos completes 3 orbits during each Martian day. The rapid orbital decay of Phobos, caused by tidal friction that robs energy from its motion, ensures that this moon will eventually either crash into Mars or break apart to form a temporary ring system within the next 50 million years, as 3i Atlas approaches its closest point to Mars, now only weeks away. The gravitational interaction between the two objects becomes strong enough to produce measurable effects on both bodies. The comet's trajectory bends slightly under Mars's influence. Though the red planet's mass, only 11% that of Earth, creates perturbations far more subtle than those produced by Jupiter's gravitational dominance. These small deflections accumulate over time according to the mathematics of orbital mechanics, potentially altering the comet's ultimate path through the inner solar system by amounts that will become significant only over periods measured in months or years. The Martian atmosphere, though tenuous compared to Earth's gaseous envelope, possesses sufficient density to create detectable interactions with the outer regions of 3i Atlas's expanding coma, at altitudes where the comet's gas cloud extends closest to Mars. Atmospheric molecules experience collisions with particles escaping from the visitor's nucleus, creating brief fluorescent events that release photons at wavelengths characteristic of carbon dioxide and nitrogen excited to higher energy states. These collisional processes, occurring in near-vacuum conditions that exist nowhere in Earth's atmosphere, provide insights into plasma physics and molecular dynamics under extreme conditions. The Martian magnetosphere, unlike Earth's global magnetic field generated by a liquid iron core, consists of localized magnetic anomalies preserved in crustal rocks from an epoch when the planet possessed a more Earth-like magnetic dynamo. These fossil magnetic fields, detected by orbiting spacecraft as patches of enhanced magnetic field strength, interact weakly with the ionized components of the comet's tail, creating perturbations that become visible to instruments designed to study space plasma physics. The interaction reveals information about both the comet's gas production rate and the strength and orientation of Mars's remnant magnetic fields. Ground-based observations from Earth reveal that the comet's dust tail, now stretching across several degrees of sky as viewed from terrestrial locations, exhibits subtle changes in brightness and colour that correspond to its changing distance from Mars. The gravitational focusing effect of the red planet's mass creates slight concentrations of dust particles along specific trajectories, producing brightness enhancements that last for days before dispersing back into the background population of comet debris. These gravitational lensing effects, operating on scales far smaller than those involved in galactic astronomy, demonstrate the universal applicability of general relativity to systems ranging from binary stars to interplanetary dust clouds. The approach to Mars also provides the first opportunity for detailed comparative spectroscopy between the comet's outgassing and the composition of Martian atmospheric gases. Water vapor escaping from 3I Atlas carries isotopic signatures that differ measurably from water detected in Mars's polar ice and atmospheric humidity, indicating that the two objects formed in stellar environments with different deuterium abundances and different exposure to cosmic ray bombardment. These isotopic differences, though measured in parts per thousand, provide crucial data for understanding the sources of water that supplied the early solar system and the processes that governed volatile delivery to the terrestrial planets. As the distance between comet and planet continues to decrease, both objects prepare for a gravitational encounter that represents the closest approach between materials from different stellar systems that has occurred in the inner solar system within recorded history. The interaction will unfold over periods measured in days but will influence the trajectories and evolution of both objects for years to come, creating observational opportunities that may not repeat for centuries and providing insights into the dynamics of small bodies in planetary encounters that bridge the gap between theoretical celestial mechanics and direct empirical observation. In the gravitational theatre surrounding Mars, where the red planet's two diminutive moons trace their swift orbits through space cleared by billions of years of tidal evolution, Phobos and Deimos prepare to witness an event unprecedented in their long existence. These captured asteroids, each bearing the scars of impacts that date to the solar system's violent youth, now find themselves positioned as silent observers of the closest approach between their adopted planet and a visitor carrying materials from another star system entirely. Phobos, the inner and larger of Mars's two moons, completes its orbital dance around the red planet in just 7 hours and 39 minutes, racing around Mars faster than the planet itself rotates. This rapid motion, unique among the large moons of the solar system, creates the bizarre phenomenon of a moon that rises in the west and sets in the east as viewed from Mars's surface, crossing the ruddy sky twice during each Martian day. The moon's irregular shape, measuring 27 by 22 by 18 kilometers, reflects its origin as a captured asteroid that never achieved the hydrostatic equilibrium necessary to form a spherical body. The surface of Phobos bears the distinctive grooves and crater chains that speak of its tortured gravitational relationship with Mars. These parallel furrows, each several hundred meters wide and extending for kilometers across the moon's battered terrain, may represent fractures created by tidal stresses as Mars's gravity slowly tears apart the loosely consolidated rubble pile that comprises the moon's interior structure. The largest crater on Phobos, named Stickney, after the wife of the moon's discoverer, measures nearly 10 kilometers across, so large relative to the moon's dimensions that the impact which created it nearly shattered the entire body into fragments. Deimos, orbiting at a more leisurely pace 23,000 kilometers above Mars's surface, presents an equally scarred visage that chronicles eons of bombardment by interplanetary debris. This outer moon, smaller than Phobos and more distant from Mars's gravitational influence, rotates synchronously with its orbital period, keeping the same face toward the planet in the same tidally locked configuration that characterizes Earth's larger moon. The synchronous rotation creates permanent day and night hemispheres on Deimos, with the Mars-facing side experiencing constant illumination from light reflected off the planet's rust-colored surface. The composition of both moons, revealed through spectroscopic analysis of reflected sunlight, closely matches that of carbonaceous chondrite meteorites, primitive rocky bodies rich in carbon compounds and hydrated minerals that formed in the cooler outer regions of the early solar system. This chemical similarity to outer solar system asteroids supports the hypothesis that Phobos and Deimos represent captured objects that originally orbited the Sun in the asteroid belt, before gravitational perturbations altered their trajectories and brought them within Mars's sphere of influence. The capture mechanism itself remains mysterious, requiring precise conditions of velocity and trajectory that seem improbable, yet must have occurred to explain the Moon's current orbital configuration. As 3I Atlas approaches its closest passage by Mars, now less than 2 million kilometers from the planet's center, the gravitational interaction between the three bodies creates a complex dynamical system that challenges the computational methods of celestial mechanics. The comet's trajectory, already modified by encounters with Jupiter and passage through the asteroid belt, undergoes additional perturbations as Mars's gravity field pulls it into a hyperbolic encounter that will sling the visitor past the planet and toward the inner solar system. These gravitational forces operate with mathematical precision, yet their cumulative effects create chaotic sensitivity to initial conditions that makes long-term trajectory prediction increasingly uncertain. The moons themselves experience subtle perturbations in their orbits, as the comet's gravitational field, though weak, adds its influence to the complex tidal environment surrounding Mars. Phobos, already spiraling slowly inward due to tidal friction that dissipates orbital energy as heat within the Moon's interior, experiences minor changes in its orbital decay rate as the passing comet creates temporary modifications in the local gravitational gradient. These perturbations, measurable only through precise timing of the Moon's orbital period, accumulate over years to produce detectable changes in Phobos's position relative to surface features on Mars. The comet's expanding coma, now reaching diameters comparable to terrestrial continents, extends far enough from the nucleus to interact gravitationally with the Martian satellite system. Gas molecules escaping from 3I Atlas at velocities of several kilometers per second create an extended atmosphere around the comet that responds to the gravitational influences of both Mars and its moons. This tenuous gas envelope, with densities billions of times lower than Earth's atmosphere, nonetheless possesses sufficient extent to experience tidal effects that stretch and compress the coma in response to the varying gravitational gradients encountered during the close approach. From the perspective of hypothetical observers stationed on Phobos or Deimos, the approaching comet would appear as a fuzzy star gradually brightening against the stellar background, its tail becoming visible as a ghostly streamer of light that grows longer and more prominent as 3I Atlas sheds increasing quantities of ancient ice into the solar wind. The tail's orientation, always pointing away from the sun regardless of the comet's direction of motion, creates geometric configurations that change daily as the comet, Mars, and the moons move through their complex orbital choreography. The radar characteristics of the Martian moons, revealed through Earth-based observations and measurements by Mars-orbiting spacecraft, indicate internal structures dominated by void spaces and loose rubble rather than solid rock. This high porosity, typical of asteroids that formed through accretion of smaller bodies rather than differentiation from molten material, makes both Phobos and Deimos vulnerable to disruption by gravitational forces that would leave more consolidated bodies unaffected. The passing comet, though lacking sufficient gravitational influence to threaten the Moon's structural integrity, creates detectable changes in their radar reflection properties as tidal forces subtly compress and expand the void spaces within their interiors. Spectroscopic monitoring of both moons during the comet's approach reveals no detectable changes in their surface composition, confirming theoretical predictions that the interaction energies involved remain far below the thresholds necessary to alter mineral structures or trigger outgassing from any volatile materials that might exist within the moon's interiors. The chemical stability of Phobos and Deimos throughout this gravitational encounter demonstrates the resilience of small rocky bodies to all but the most extreme perturbations, a characteristic that has allowed asteroids and comets to preserve primordial materials essentially unchanged for billions of years. The orbital mechanics governing this three-body encounter follow the same mathematical principles that describe binary star systems, planetary ring dynamics, and the formation of galaxy clusters, yet operate here on scales that make direct observation and measurement possible with existing technology. The precision of gravitational theory, validated through centuries of solar system observations, predicts the outcome of this encounter with accuracies measured in kilometers and seconds, demonstrating the universality of physical laws that govern phenomena ranging from subatomic particles to cosmological structures. As the moment of closest approach draws near, the Martian system prepares to experience the gravitational signature of materials that formed around another star, a brief encounter between objects that represent different epochs of galactic evolution and stellar chemistry. The moons of Mars, themselves relics of the early solar system's chaotic dynamics, serve as witnesses to this meeting between ancient travelers, their scarred surfaces recording through gravitational memory the passage of a visitor that carries within its nucleus the chemical fingerprints of stellar processes that operated when the galaxy was younger, and star formation followed different patterns than those that govern the current epoch of cosmic evolution. Above the ancient riverbeds and dried lake shores of Mars, where evidence of vanished waters lies etched in stone like fossilized memories of a more temperate world, the planet's gossamer atmosphere holds within its thin embrace traces of the hydrological cycle that once transformed this world into something resembling Earth. The atmospheric pressure on Mars, barely 1% that of Earth's sea level environment, creates conditions where water can exist as liquid only in the deepest valleys and only during the warmest parts of the Martian summer. Yet this tenuous gaseous envelope preserves chemical evidence of epochs when rivers carved valleys and lakes filled with water, deep enough to support sedimentary processes that operated for millions of years. The composition of Mars's atmosphere, dominated by carbon dioxide with traces of nitrogen, argon, and water vapor, tells the story of atmospheric evolution that began when the planet possessed a thicker gaseous envelope capable of supporting liquid water at its surface. Isotopic ratios of atmospheric gases reveal the signature of preferential loss of lighter isotopes to space, a process that occurs when solar ultraviolet radiation dissociates water molecules in the upper atmosphere and allows hydrogen atoms to escape Mars's relatively weak gravitational field. The deuterium to hydrogen ratio in Martian water vapor, enriched in the heavier isotope by factors that indicate billions of years of selective hydrogen loss, provides a quantitative measure of how much water the planet has lost to space since its formation. Seasonal variations in atmospheric composition create global changes that would be immediately apparent to any hypothetical observer stationed on the planet's surface. During the Northern Hemisphere's winter, carbon dioxide condenses at the polar ice cap in quantities sufficient to reduce global atmospheric pressure by nearly 30%, creating the most dramatic seasonal pressure changes known in the solar system. This massive redistribution of atmospheric mass drives wind systems that can generate planet-wide dust storms, events so extensive they obscure the entire planetary surface for months and can be observed from Earth-based telescopes as temporary changes in Mars's overall brightness and colour. The water vapour content of Mars's atmosphere, though measured in parts per million rather than the percentages that characterise Earth's humidity, fluctuates with seasons and locations in patterns that reflect the complex interactions between surface ice deposits, atmospheric circulation, and the sublimation of water from permafrost layers that may extend to depths of several kilometres below the surface. Morning fogs form in Martian valleys when overnight cooling allows water vapour to condense into ice crystals, creating atmospheric phenomena that superficially resemble terrestrial weather but operate under physical conditions so extreme that the familiar processes of meteorology take on alien characteristics. As 3i Atlas approaches its closest passage by Mars, now mere days away from the encounter, the interaction between the comet's expanding coma and Mars's thin atmosphere begins to produce detectable effects that provide insights into both objects' physical properties. The outer regions of the comet's gas envelope, extending millions of kilometers from the nucleus, encounter atmospheric molecules at altitudes where the Martian exosphere transitions into interplanetary space. These collisions, occurring at relative velocities of tens of kilometers per second, create brief fluorescent events that release photons at wavelengths characteristic of atmospheric gases excited to higher energy states by impact with high-velocity comet particles. The chemical signatures emerging from these atmospheric interactions reveal subtle differences between the water vapour in Mars's atmosphere and the sublimating ice from 3I Atlas. Isotopic analysis of the fluorescent emissions shows that the comet's water possesses deuterium ratios that differ significantly from Martian atmospheric water, indicating formation in stellar environments where cosmic ray bombardment and stellar wind composition created different conditions for isotopic fractionation. These measurements provide comparative data that illuminates the sources of water that supplied both the early Mars and the interstellar medium from which the comet condensed around another star. The dust component of Mars's thin atmosphere, consisting of particles so fine they remain suspended for months after dust storms and create the reddish haze that colours Martian sunsets, interacts weakly but measurably with the comet's dust tail through electromagnetic forces that operate over interplanetary distances. The electrostatic charging of dust particles in Mars's atmosphere, caused by friction during wind transport and exposure to solar ultraviolet radiation, creates fields that can influence the trajectories of similarly charged particles in the comet's tail, producing subtle deflections that become visible to instruments designed to study particle dynamics in space environments. Atmospheric escape from Mars. The ongoing process by which the planet continues to lose its gaseous envelope to space accelerates slightly during the comet's close approach due to the additional heating caused by collisions between atmospheric molecules and high-velocity particles from the comet's coma. The energy deposited by these collisions, though minimal compared to solar heating, creates temporary increases in upper atmospheric temperatures that enhance the rate at which hydrogen and other light elements achieve escape velocity and leave the planet permanently. These transient changes in escape rate, detectable through measurements of atmospheric glow at specific ultraviolet wavelengths, provide insights into the mechanisms that have shaped Mars's atmospheric evolution over geological time. The thin Martian atmosphere also serves as a natural laboratory for studying the behavior of comet gases under conditions that exist nowhere else in the solar system. The low atmospheric pressure allows comet particles to penetrate deeper into Mars's gaseous envelope than would be possible in Earth's denser atmosphere, creating interaction zones where the physics of gas dynamics operate under extreme conditions that bridge the gap between atmospheric science and vacuum physics. These hybrid environments, characterized by pressures and densities that fall between those of planetary atmospheres and interplanetary space, reveal how familiar physical processes adapt to conditions that exist at the boundaries of conventional scientific categories. Trace constituents of Mars's atmosphere, including methane detected in concentrations of a few parts per billion, may experience temporary enhancements during the comet's passage as organic compounds from 3I Atlas undergo photodissociation in the Martian upper atmosphere. The methane in Mars's atmosphere, whether of biological or geological origin, represents one of the planet's most intriguing chemical mysteries, since this molecule should be destroyed by atmospheric chemistry processes within a few hundred years unless it is continuously replenished by active sources. The interaction with organic compounds from an interstellar comet provides a natural experiment in comparative atmospheric chemistry that may illuminate the processes responsible for methane production on Mars, the aurora phenomena occasionally observed in Mars's thin atmosphere, caused by interactions between solar wind particles and the planet's patchy magnetic field, may be enhanced during the comet's close approach, as the additional charge particles in the comet's ionized tail interact with Mars's remnant magnetosphere. These auroral displays, visible primarily at ultraviolet wavelengths due to the low density of atmospheric gases, create temporary light shows that operate according to the same physical principles that generate Earth's northern and southern lights, but under atmospheric conditions so tenuous that the familiar green and red colours of terrestrial aurora are replaced by ultraviolet emissions invisible to hypothetical human observers on the Martian surface. The atmospheric dynamics of Mars, driven primarily by solar heating and the sublimation of polar ice deposits, experience subtle modifications during the comet's passage, as the additional heating from comet particle impacts creates temporary pressure gradients that influence wind patterns and atmospheric circulation. These changes, though small compared to the seasonal variations that characterize Martian meteorology, demonstrate the sensitivity of thin planetary atmospheres to external perturbations and provide insights into how atmospheric systems respond to transient energy inputs from space-based sources. As 3i Atlas prepares for its closest approach to Mars, the red planet's thin atmosphere stands ready to record through chemical and physical changes the passage of materials that formed under the skies of another world, creating a temporary bridge between stellar environments separated by light years of space and millions of years of galactic evolution. At 14:37 Universal Time on a Tuesday afternoon that will be recorded in astronomical annals as a moment of unprecedented scientific opportunity, 3i Atlas sweeps past Mars at its point of closest approach, the two objects separated by a distance of 1.84 million kilometers, less than 5 times the span between Earth and its moon, yet representing the nearest encounter between materials from different stellar systems that has occurred within the observational reach of human instruments. The geometry of this celestial rendezvous, dictated by the inexorable mathematics of orbital mechanics and gravitational dynamics, creates viewing angles and measurement opportunities that will not repeat for millennia, if ever, given the hyperbolic trajectory that will carry the interstellar visitor beyond the gravitational boundaries of our solar system and back into the cosmic dark. The relative velocity between comet and planet at closest approach measures 23.7 kilometers per second, a speed that reflects the visitor's interstellar origins and its trajectory through gravitational fields that have accelerated it toward the inner solar system. This velocity, nearly 70 times faster than a rifle bullet, represents the vector sum of the comet's original motion through galactic space and the gravitational acceleration imparted by the Sun's influence during its inbound journey. At such speeds, the encounter unfolds with temporal rhythms that compress months of approach into hours of closest interaction, creating observational windows that demand precise coordination between Earth-based telescopes and spacecraft positioned throughout the solar system. From Mars's perspective, the comet appears to sweep across the sky with angular velocity measured in arc-minutes per hour, fast enough that its motion would be apparent to hypothetical observers on the planet's surface watching through telescopes, yet slow enough that detailed spectroscopic observations can track changes in the comet's outgassing as it responds to the varying gravitational and thermal environment of the encounter. The comet's tail, now stretching across more than 10 degrees of sky as viewed from Mars, exhibits subtle changes in brightness and structure that reflect the complex interplay between solar radiation pressure, the comet's own gas production, and the gravitational influence of the red planet's mass. The gravitational interaction between the two objects creates tidal forces that, though weak compared to those experienced by bodies in close binary star systems, nonetheless produce measurable effects on the comet's nucleus and extended atmosphere. The differential gravitational pull between the side of the comet facing Mars and the side facing away creates stresses that may trigger changes in the outgassing rate, as the nucleus responds to forces it has not experienced since leaving its birth stellar system millions of years ago. These tidal effects operate according to the same physical principles that drive volcanic activity on Jupiter's moon Io, and create the twice-daily ocean tides on Earth. But here they act on a body composed primarily of ice and dust rather than rock and magma. Seismic monitoring stations on Mars, originally designed to detect Marsquakes and meteorite impacts, record subtle vibrations that may result from the gravitational influence of the passing comet. These signals, buried in data that require sophisticated analysis to separate from background noise caused by thermal expansion of surface rocks and atmospheric pressure variations, represent the first attempt to detect gravitational effects through seismology on a planet other than Earth. The amplitude of any comet-induced seismic signals would be extraordinarily small, requiring signal processing techniques that push the boundaries of current geophysical instrumentation. Yet their detection would provide unprecedented insights into both Mars's internal structure and the comet's mass distribution. Radio telescopes on Earth, working in coordination with spacecraft positioned throughout the solar system, conduct simultaneous observations that create an interferometric baseline stretching across interplanetary distances. This distributed observatory, with resolution capabilities that exceed those of any single instrument, maps the structure of the comet's coma and tail with precision sufficient to detect changes occurring over timescales of hours as the encounter reaches its climax. The data streams from these observations, transmitted across space at the speed of light, create computational challenges that require supercomputing resources to process and analyze in near real time. The comet's dust tail, sculpted by radiation pressure from sunlight and charged particle impacts from the solar wind, exhibits temporary focusing effects as Mars's gravitational field creates slight concentrations of particles along specific trajectories. These gravitational lensing phenomena, operating on scales far smaller than those involved in cosmological observations of distant galaxies, nonetheless demonstrate the universal applicability of general relativity to systems ranging from interplanetary dust clouds to galactic clusters. The focusing effects create temporary brightness enhancements in the tail that persist for several hours before dispersing back into the background population of comet debris. Spectroscopic analysis during closest approach reveals the most detailed chemical inventory yet obtained of materials from another stellar system. The high-resolution spectra show absorption and emission lines corresponding to molecular species that formed under stellar radiation conditions, different from those in our local galactic neighborhood, providing insights into stellar nucleosynthesis and chemical evolution processes that operated when different populations of stars dominated the local stellar environment. Water molecules escaping from the comet's nucleus carry isotopic signatures that encode information about cosmic ray bombardment rates and stellar wind composition in the interstellar medium through which 3I Atlas travelled during its journey between star systems. The encounter provides the first opportunity for comparative measurements of gravitational effects on cometary outgassing, as the comet's response to Mars's gravitational field can be compared with theoretical predictions and previous observations of solar system comets in similar circumstances. The rate of gas production from the nucleus, measured through monitoring of specific spectral lines, shows variations that correlate with the changing gravitational gradient as the comet follows its hyperbolic trajectory past the planet. These variations, though subtle, provide information about the internal structure and mechanical properties of cometary nuclei that cannot be obtained through remote observations alone. Mars-orbiting spacecraft, positioned to observe the encounter from close range, detect changes in the planet's exospheric properties as the comet's extended coma interacts with the outermost regions of the Martian atmosphere. The collision cross-sections involved in these interactions, though operating at molecular scales, accumulate over the vast volumes of space involved to create detectable modifications in atmospheric composition and temperature structure. These changes, temporary and subtle, nonetheless provide insights into atmospheric escape processes and the response of planetary exospheres to transient external perturbations. The magnetic field measurements conducted by spacecraft throughout the Mars system reveal complex interactions between the comet's ionized tail and the remnant magnetic fields preserved in Mars's crustal rocks. These fossil magnetic anomalies, relics of an epoch when Mars possessed a global magnetic dynamo similar to Earth's, create localized distortions in the interplanetary magnetic field that influence the trajectory of charged particles in the comet's tail. The resulting magnetic signatures, recorded at multiple locations throughout the encounter, provide information about both the comet's plasma production rate and the strength and orientation of Mars's ancient magnetic field. As the moment of closest approach passes and the distance between comet and planet begins to increase, both objects carry with them the gravitational memory of this brief encounter. The comet's trajectory, now slightly modified by Mars's influence, will carry it toward the inner solar system along a path that differs measurably from its pre-encounter orbit. While Mars continues its eternal circuit around the Sun, with orbital elements that bear the infinitesimal signature of having hosted a visitor from the stars, beyond the point of closest approach, where gravitational mathematics dictated the precise geometry of encounter between worlds born under different suns. 3I Atlas begins its measured retreat from Mars with the same inexorable momentum that carried it through the outer reaches of interstellar space for millions of years. The comet's trajectory, now permanently altered by its gravitational dance with the red planet, follows a hyperbolic path that will carry it deeper into the inner solar system before eventually returning it to the cosmic dark from which it emerged, bearing within its nucleus both the chemical memories of another stellar system and the gravitational signatures of its passage through ours. The physics governing this outbound phase of the encounter mirror those of the approach, yet in reverse temporal sequence, creating a symmetry that reflects the time-reversible nature of gravitational dynamics under conditions where relativistic effects remain negligible. These same tidal forces that stretched and compressed the comet's nucleus during closest approach now relax with equal precision, allowing the ancient ice to return to its equilibrium configuration as the influence of Mars's gravity field diminishes with increasing distance. This relaxation process occurs according to the material properties of ice subjected to stresses over timescales that bridge the gap between laboratory measurements and geological processes. The comet's tail, that ephemeral structure composed of gas and dust liberated from ice that froze around another star, now streams behind the nucleus in the classic configuration that gives comets their distinctive appearance in telescopic observations. The tail's orientation, always pointing away from the sun regardless of the comet's direction of motion, creates the counterintuitive phenomenon of a comet that appears to be fleeing backwards from its own debris as it recedes from Mars and heads toward the inner regions of our solar system. This geometric arrangement, dictated by the physics of radiation pressure and solar wind dynamics, transforms 3I Atlas from an approaching visitor into a departing messenger, trailing ancient materials across interplanetary space. Spectroscopic monitoring of the comet's continued outgassing reveals subtle changes in composition as different layers of the nucleus sublimate in response to increasing solar heating. Materials that condense during different epochs of the comet's formation around its parent star become accessible to sublimation as surface layers boil away, creating a temporal sequence of chemical signatures that provides insights into the physical conditions that existed in another stellar system over extended periods of time. Each new spectral line that appears in the comet's spectrum represents the liberation of molecular species that have remained frozen since the epoch when mammoths roamed Earth and ice ages shaped terrestrial climate patterns. The dust production rate from the comet's nucleus increases measurably as it moves close to the Sun, following power laws that govern the sublimation of volatile ices under increasing thermal stress. This enhanced dust emission, driven by the sublimation of water ice and other volatiles that remain stable only at the low temperatures of the outer solar system, creates a more prominent dust tail that becomes increasingly visible to Earth-based observers as 3I Atlas continues its inbound journey. The dust grains themselves, each carrying the mineralogical signature of condensation processes that occurred in the disk of another star, scatter sunlight with efficiencies that depend on their size, distribution, and chemical composition. Radio observations reveal changes in the comet's radar reflection properties as solar heating modifies the physical structure of its surface layers. The dielectric constant of the nucleus material, altered by the phase transitions that occur as various ices sublimate and leave behind refractory residues, creates time-variable radar signatures that provide information about subsurface layering and composition gradients within the comet's interior. These measurements, conducted using the most sensitive planetary radar systems on Earth, push the boundaries of what can be determined about small solar system bodies through remote sensing techniques. The interaction between the comet's expanding coma and the solar wind becomes increasingly complex as 3I Atlas approaches regions where the density and velocity of charged particles from the Sun create more dynamic plasma environments. Ion-neutral chemical reactions, occurring in gas densities that remain far below terrestrial atmospheric conditions yet far exceed those of interstellar space, produce secondary chemical species that create their own spectral signatures and provide insights into plasma chemistry processes that operate under conditions unique to cometary environments. These reactions follow the same principles that govern chemistry in laboratory plasmas and stellar atmospheres, yet operate here in parameter ranges that exist nowhere else in the accessible universe. Ground-based telescopes tracking the comet's progress detect increasing variability in its brightness and spectral characteristics, as the nucleus responds to the growing intensity of solar heating through mechanisms that may include seasonal changes in the sublimation rate from different hemispheres, rotational effects that expose different compositional regions to sunlight, and possible fragmentation events that could split the nucleus into multiple components. This variability, characteristic of many comets as they approach the inner solar system, reflects the mechanical instability of objects composed primarily of ice and dust when subjected to thermal stresses that vary by orders of magnitude over relatively short time periods. The comet's orbital velocity, now increased by gravitational acceleration during its passage through the inner regions of Mars's influence, carries it toward future encounters with the inner planets at speeds that will create even more dramatic observational opportunities and scientific challenges. The kinetic energy gained during the Mars encounter, though small compared to the comet's total orbital energy, nonetheless represents a permanent change in its trajectory that demonstrates the cumulative effects of gravitational interactions in determining the long-term evolution of small body orbits throughout the solar system. Atmospheric scientists studying the residual effects of the comet's passage near Mars detect subtle changes in the red planet's exospheric composition that persist for weeks after the encounter, indicating that the interaction between comet gases and planetary atmospheric constituents created chemical products with longer lifetimes than he initially predicted by theoretical models. These persistent signatures provide natural experiments in atmospheric chemistry that reveal how planetary atmospheres respond to transient chemical inputs from external sources, processes that may have been important during epochs when comet bombardment rates were higher and atmospheric evolution proceeded under different boundary conditions. The scientific data streams generated during the encounter, now flowing from telescopes and spacecraft throughout the solar system to data processing centers on Earth, create computational challenges that require months or years of analysis to fully exploit. The multispectral observations, radar measurements, gravitational perturbation studies, and plasma physics experiments conducted during the closest approach phase generate datasets that will support research programs for decades, providing insights into comparative planetology, stellar nucleosynthesis, galactic chemical evolution, and the physics of small bodies that bridge the gap between solar system science and astrophysics. As 3i Atlas continues its outbound journey from Mars, now carrying the gravitational memory of its encounter with our solar system's fourth planet, it serves as a travelling laboratory that will provide continuing opportunities for scientific observation as it approaches Venus, Mercury, and eventually the Sun itself. The comet's trajectory, now precisely determined through the tracking data obtained during the Mars encounter, can be predicted with sufficient accuracy to plan future observational campaigns that will exploit its passage through different regions of the inner solar system to conduct comparative studies of cometary behavior under varying thermal and gravitational conditions across the expanses of space that separate Mars from Earth, where radio waves carrying scientific data traverse distances measured in light minutes. Telescopes scattered across the third planet's night hemisphere turn their collective gaze toward the retreating visitor from interstellar space. The global network of observatories, coordinated through timing systems synchronized to atomic clocks and linked by data networks that span continents, focuses its combined optical and electronic senses on 3i Atlas as it begins its journey deeper into the solar system's interior regions, carrying with it the gravitational signatures of its encounter with Mars and the slowly evolving chemistry of ancient ice yielding to solar heat. The Atacama Desert, where atmospheric conditions create some of Earth's clearest skies and driest air, hosts radio telescope arrays that detect the faint whispers of molecular emission from the comet's expanding coma at wavelengths that penetrate Earth's atmosphere with minimal absorption. These instruments, operating in the millimeter and submillimeter portions of the electromagnetic spectrum, reveal spectral lines corresponding to carbon monoxide, methanol, and other organic compounds that sublimate from ice matrices that formed in temperatures colder than liquid nitrogen around a star whose light has never reached our telescopes. The molecular transitions detected in these observations encode information about rotational and vibrational energy states that reflect the physical conditions existing within the comet's nucleus. As solar heating drives phase changes in materials that have remained unchanged for millions of years, observatory complexes perched on volcanic peaks in Hawaii and the Canary Islands exploit the thin, stable atmosphere at high altitude to conduct optical and infrared observations that track changes in the comet's dust production as it responds to increasing solar heating. The thermal infrared signatures, invisible to human vision but readily detectable by instruments cooled to liquid nitrogen temperatures, reveal the size distribution and mineralogy of dust grains ejected from the nucleus at velocities measured in hundreds of meters per second. These particles, each no larger than cigarette smoke yet carrying within their crystalline structure the chemical fingerprints of mineral formation processes that occurred in the disk of another star, create emission features at wavelengths that correspond to molecular vibrations in silicate lattices and organic carbon compounds. The coordinated observation campaigns require precise timing that accounts for the finite speed of light across interplanetary distances, ensuring that measurements conducted simultaneously from multiple Earth-based locations actually sample the same physical phenomena occurring around the comet, despite the 17-minute delay for radio signals to traverse the space between 3i Atlas and terrestrial receivers. This temporal synchronization, achieved through GPS satellite networks and atomic clock standards that maintain accuracy better than 1 part in 10 billion, creates a distributed observatory with angular resolution capabilities that exceed those of any single telescope through the interferometric combination of signals received at widely separated locations. Space-based telescopes, operating beyond the distorting effects of Earth's atmosphere, provide complementary observations at ultraviolet and X-ray wavelengths that reveal the highest energy processes occurring as solar wind particles interact with ionized gases in the comet's tail. The Hubble Space Telescope, with its unprecedented angular resolution and sensitivity to ultraviolet emissions that cannot penetrate to Earth's surface, detects fluorescence from water vapor molecules excited by solar ultraviolet radiation, creating spectral signatures that encode information about the isotopic composition of water ice that formed under the stellar radiation environment of another sun. These observations provide direct measurements of deuterium to hydrogen ratios that offer insights into stellar nucleosynthesis and galactic chemical evolution processes that operated in different regions of the galaxy during earlier epochs of cosmic history. The tracking data obtained through radar observations conducted by the world's most powerful planetary radar systems, including the Arecibo Observatory and the Goldstone Deep Space Communications Complex, provide measurements of the comet's distance and radial velocity with precision approaching centimeters per second. These radar techniques, which involve transmitting high-power radio signals toward the comet and analyzing the characteristics of the reflected echoes, reveal information about the nuclear surface properties, internal structure, and rotation state that cannot be obtained through passive optical observations alone. The radar cross-section measurements indicate surface roughness and dielectric properties that reflect the mechanical and chemical evolution of materials subjected to millions of years of cosmic ray bombardment and micrometeorite impacts during the comet's journey through interstellar space. Photometric monitoring programs, using automated telescopes that measure the comet's brightness at multiple wavelengths throughout each night of observation, detect periodic variations that correspond to the nucleus rotation period and reveal non-uniform surface properties that create changes in reflectivity and outgassing rate as different hemispheres face toward the sun. These brightness variations, with amplitudes measured in hundredths of a magnitude, require photometric precision that demands careful calibration against standard stars and correction for atmospheric extinction effects that vary with the comet's changing position in Earth's sky. The rotational light curves derived from these measurements provide insights into the comet's shape, surface composition gradients, and the distribution of volatile materials within the nucleus that drive the observed outgassing patterns. Spectroscopic observations conducted at wavelengths spanning from radio to gamma rays create comprehensive chemical inventories that reveal not only the major constituents of the comet's nucleus, but also trace species present at concentration levels measured in parts per million. The detection of isotopic variants of common molecules, including heavy water containing deuterium and carbon compounds enriched in carbon-13, provides quantitative constraints on the stellar nucleosynthesis processes that produce the raw materials from which 3I Atlas condensed in another stellar system. These isotopic signatures, preserved in ice matrices that have remained chemically inert during the comet's interstellar journey, offer direct samples of stellar wind and supernova ejecta that enrich the interstellar medium in different regions of the galaxy during epochs when star formation rates and stellar population characteristics differed from those observed in our current galactic neighborhood. The global coordination of these observational programs requires international cooperation that transcends political boundaries and time zones, creating scientific collaborations that unite astronomers working under different national research programs, yet sharing common goals of understanding the physical processes that govern cometary evolution and the chemical signatures that preserve information about stellar evolution in distant regions of the galaxy. The data-sharing protocols established for the 3I Atlas observational campaign create precedents for future studies of interstellar visitors and demonstrate the scientific benefits that emerge when the global astronomical community functions as a coordinated international observatory rather than a collection of independent national research programs. Amateur astronomers, equipped with increasingly sophisticated commercial telescopes and electronic cameras, contribute their own observations to the coordinated tracking effort, providing temporal coverage that fills gaps in the professional observatory schedules and extending the geographical distribution of observation sites to regions not served by major research institutions. These citizen science contributions, though individually less precise than data obtained with research-grade instrumentation, collectively provide statistical sampling that improves the overall quality of the dataset and demonstrates the continued importance of amateur participation in astronomical research programs that study phenomena visible through moderate-sized telescopes under suitable observing conditions, as 3I Atlas continues its retreat from Mars and approach toward the inner solar system. The accumulated observational data creates an increasingly detailed portrait of an object that carries within its nucleus materials older than any terrestrial rock and chemical signatures that encode the nuclear history of stellar processes that operated in different regions of the galaxy during epochs when the universe was younger and galactic evolution followed different patterns than those observed in the current cosmological era. In the vast reaches of space between Mars and Venus, where the solar wind gains intensity and the sun's gravitational pull becomes increasingly dominant in the dynamics of small bodies. The coma surrounding 3I Atlas begins its slow dissolution as the comet moves beyond the optimal distance for sustained gas production from its ancient nucleus. The Gossamer atmosphere that once extended across millions of kilometers, creating a temporary world composed entirely of sublimated ice and liberated dust, now contracts and fades as the balance of physical forces shifts away from the conditions that supported its spectacular growth during the approach to Mars. The process unfolds with the same inexorable logic that governs all phase transitions in the universe, from the condensation of water vapor in terrestrial clouds to the sublimation of carbon dioxide at the polar caps of Mars. As 3I Atlas continues its trajectory deeper into the solar system, the increasing solar radiation that drives enhanced outgassing from its nucleus also creates the radiation pressure and charged particle environment that strips away the very gases that sublimation produces. This paradoxical relationship between the energy source that creates the coma and the forces that ultimately destroy it reflects the complex feedback mechanisms that govern the evolution of cometary atmospheres throughout their passages around stars. The outer boundaries of the coma, where gas densities fall below 1 molecule per cubic centimetre, begin to merge imperceptibly with the interplanetary medium through processes that operate on scales ranging from individual molecular collisions to the bulk flow of plasma across magnetic field lines embedded in the solar wind. The transition zone between cometary atmosphere and space represents neither a sharp boundary nor a gradual fade, but rather a complex interface, where different physical processes dominate at different scales and under different conditions of local particle density and magnetic field strength. Hydrogen atoms, the lightest constituents of the disintegrating coma, escape most readily from the comet's weakening gravitational influence, achieving velocities that carry them far beyond the nucleus before solar ultraviolet radiation ionizes them and incorporates them into the general population of charged particles that comprise the solar wind. These hydrogen atoms, originally locked in water ice molecules that formed in the protoplanetary disk of another star, now join the continuous outflow of matter from our own Sun that pervades the entire heliosphere and eventually reaches the boundary where solar influence merges with the interstellar medium from which the comet originally emerged. The spectroscopic signatures of molecular species in the coma fade in inverse correlation with their molecular masses and binding energies, creating a temporal sequence of disappearance that provides insights into the physical chemistry of gas phase reactions under conditions that exist nowhere else in the accessible universe. Water vapor, with its relatively high molecular weight and strong hydrogen bonding characteristics, persists longer in detectable concentrations than the lighter molecules like carbon monoxide and nitrogen that were among the first species to appear when the coma initially formed. This mass-dependent fractionation creates changing isotopic ratios in the observable gas as lighter isotopic variants escape preferentially, leaving behind samples enriched in heavier isotopes that record the final stages of cometary atmospheric evolution. The dust component of the fading coma follows different evolutionary pathways that depend on particle size, composition, and the mechanical properties that determine how individual grains respond to radiation pressure from sunlight and momentum transfer from solar wind particles. Larger dust grains, those approaching the dimensions of sand particles, fall back toward the nucleus under the influence of the comet's weak gravitational field, creating a temporary dust atmosphere that may persist for months after the gas component has dissipated below detectable levels. Smaller particles, with surface area to mass ratios that make them susceptible to radiation pressure effects, continue to accelerate away from the comet and eventually join the general population of interplanetary dust that pervades the solar system. Radio telescopes monitoring the comet's molecular emissions detect the gradual disappearance of spectral lines that once provided detailed chemical inventories of materials formed around another star. The signal strengths diminish according to power laws that reflect the physical processes governing molecular escape from the coma, creating fade rates that can be used to infer the comet's mass loss rate and the efficiency of various gas production mechanisms operating within the nucleus. These measurements provide quantitative data about cometary evolution that complement theoretical models of how icy bodies respond to solar heating as they follow trajectories that carry them through different thermal environments. Optical observations reveal changes in the apparent size and brightness of the coma that follow predictable patterns based on the geometry of solar illumination and the viewing angle from Earth-based telescopes. The angular diameter of the visible coma shrinks as its actual physical extent decreases, yet the surface brightness may increase temporarily as the same amount of light becomes concentrated into a smaller apparent area. These photometric changes, measured through careful comparison with background stars whose brightnesses remain constant, provide information about the total gas and dust production rates that cannot be obtained through spectroscopic techniques alone. The comet's tail, that most visually dramatic component of its appearance during the active phase near Mars, also begins to fade as the supply of new material from the nucleus diminishes and existing tail material disperses according to the complex dynamics of plasma and dust in the solar wind environment. The gas tail, composed primarily of ionized molecules that follow magnetic field lines, fades more rapidly than the dust tail because ionized species respond more directly to changes in the comet's gas production rate. The dust tail, with its curved geometry that reflects the mechanical effects of radiation pressure on particles of different sizes, persists longer but gradually disperses as individual dust grains follow slightly different trajectories that spread the tail material across increasingly large volumes of space. Theoretical models of cometary coma evolution, validated through comparison with the observational data obtained during 3 Atlas's active phase, predict that detectable gas production should cease entirely when the comet reaches distances from the Sun where solar heating becomes insufficient to drive sublimation from the major volatile constituents that comprise the nucleus. This transition from active comet to dormant nucleus occurs at different heliocentric distances for different volatile species, creating a complex evolutionary sequence where various components of the original coma disappear at predictable points along the comet's trajectory. The magnetic field measurements conducted by spacecraft positioned throughout the inner solar system reveal the gradual disappearance of the distinctive magnetic signatures that characterize the comet during its active phase near Mars. The bow shock that formed when the solar wind encountered the comet's expanding atmosphere weakens and eventually disappears entirely as the gas production rate falls below the threshold necessary to create significant interactions with the interplanetary magnetic field. This transition marks the transformation of 3I Atlas from an active comet with its own temporary magnetosphere to a passive object that interacts with the solar wind only through the electromagnetic properties of its nucleus surface, as the last traces of the coma fade into the background noise of interplanetary space. 3I Atlas undergoes the fundamental transformation from a world with its temporary atmosphere to a bare nucleus that will continue its journey through the inner solar system as a dark, inactive body, indistinguishable from asteroids except for the chemical composition revealed through spectroscopic analysis of its surface materials. This metamorphosis, from spectacular celestial beacon to inconspicuous interplanetary wanderer, demonstrates the temporary nature of cometary activity and the environmental sensitivity of objects composed primarily of volatile materials that exist in stable form only under the extreme conditions of interstellar space. Beyond the asteroid belt and past the orbit of Mars, where the gravitational influence of the Sun begins to weaken and the solar wind disperses into the vast emptiness between planetary systems, 3I Atlas carries within its now dormant nucleus a cargo more precious than any terrestrial treasure: microscopic particles of dust from our solar system, incorporated into its structure during the brief months when its coma expanded to planetary dimensions and swept up material that has orbited our star since the epoch of planetary formation 4.5 billion years ago. This inadvertent collection process, governed by the same collision dynamics that operate in planetary ring systems and protoplanetary disks, transforms the interstellar visitor into an unwitting messenger that will carry samples of our solar system's chemistry back into the galactic void. The dust particles embedded in the comet's outer layers during its passage through the inner solar system represent a cross-section of materials that recorded different epochs of our Sun's evolution and the chemical processing that occurred within the solar nebula during the era of planetary accretion. Microscopic fragments of asteroidal material, created by countless collisions within the asteroid belt over billions of years, now reside alongside grains of cometary dust from objects that formed in the outer reaches of the solar system and have periodically returned to the inner regions throughout the Sun's main sequence lifetime. Iron-nickel particles from metallic asteroids mix with silicate grains from rocky bodies, while organic compounds from short-period comets combine with refractory materials that condensed from the hottest regions of the primitive solar nebula. The incorporation mechanism operates through electrostatic attraction and mechanical impaction as the comet's expanding coma encounters the sparse but omnipresent population of interplanetary dust that pervades the space between planetary orbits. Individual dust grains, travelling at relative velocities measured in kilometers per second, embed themselves in the porous ice matrix of the comet's surface layers through impact processes that occur at energies sufficient to create temporary plasma conditions but insufficient to completely vaporize either the impacting particles or the target material. These micro-impacts, each involving masses measured in picograms, collectively alter the composition of the comet's outer layers in ways that will preserve a record of its passage through our solar system long after it has returned to interstellar space. Spectroscopic analysis of light reflected from the comet's nucleus during its active phase revealed the gradual appearance of absorption features that correspond to minerals characteristic of inner solar system materials, confirming that the dust incorporation process operates with sufficient efficiency to create detectable changes in surface composition over the timescales of months rather than geological ages. The ion absorption bands that appear in near-infrared spectra indicate the presence of metallic particles that could only have originated from the differentiated cores of asteroids, while the silicate features suggest incorporation of rocky materials that formed under oxidizing conditions characteristic of the inner solar system, rather than the reducing environment where the comet originally condensed. The isotopic signatures of incorporated solar system materials, though present in concentrations too low for direct measurement with current instrumentation, will gradually mix with the comet's original inventory of interstellar isotopes through physical processes that operate on molecular scales within the ice matrix. Cosmic ray bombardment during the comet's future journey through galactic space will create secondary nuclear reactions that blur the distinction between materials from different stellar environments. Yet statistical analysis of large populations of decay products may still preserve evidence of the isotopic mixing that occurred during the comet's brief sojourn within our solar system. The thermal cycling experienced by the comet's nucleus during its approach to the Sun and subsequent retreat creates physical conditions that promote the incorporation of foreign materials through processes analogous to the zone refining techniques used in materials science to purify semiconductors and other high-technology materials. The repeated sublimation and recondensation of volatile ices creates concentration gradients and phase boundaries that can trap foreign particles and incorporate them into the comet's permanent structure through mechanisms that operate more efficiently than simple mechanical impaction or electrostatic capture. As 3I Atlas continues its journey away from the Sun, now moving at velocities that exceed the escape speed from the solar system by comfortable margins, it serves as an unintentional space probe that will carry samples of our stellar environment into regions of the galaxy where no human-made spacecraft will travel for millions of years, if ever. The dust particles embedded in its nucleus will accompany the comet through encounters with interstellar clouds, passages near other stellar systems, and exposure to cosmic ray bombardment rates that vary as the comet traverses different regions of the galactic disk and halo. The long-term evolution of these incorporated materials follows physical and chemical pathways that depend on the radiation environment and temperature conditions that the comet will encounter during its journey through interstellar space. Cosmic ray spallation reactions will gradually alter the nuclear composition of heavy elements, creating isotopic signatures that record the integrated exposure history of materials that originated in our solar system but evolved under the influence of galactic cosmic rays during transit through different regions of the local stellar neighborhood. Theoretical models of galactic dynamics predict that 3I Atlas will require millions of years to traverse the distance to the nearest stellar systems, during which time gravitational perturbations from passing stars and encounters with interstellar clouds may alter its trajectory in ways that determine which stellar environments it eventually visits. The embedded solar system materials will thus serve as chemical tracers that could potentially provide future civilizations with information about the composition and isotopic characteristics of our Sun and planetary system. Assuming that sufficiently advanced analytical techniques could detect and decode the signatures of materials that comprise only trace fractions of the comet's total mass, the reciprocal process operates in the opposite direction, as solar system objects gradually acquire dust from interstellar sources through the same collision and incorporation mechanisms that allowed 3I Atlas to collect our materials. Asteroids, comets, and even planetary atmospheres receive continuous inputs of interstellar dust that carry chemical signatures from distant stellar environments, creating a slow but persistent mixing of materials between different stellar systems that operates over galactic timescales. This exchange process, mediated by objects like 3I Atlas that traverse the boundaries between stellar gravitational domains, represents a form of chemical communication between stars that has operated throughout the history of the galaxy. The scientific implications of this material exchange process extend beyond simple chemical mixing to encompass possibilities for the transfer of complex organic compounds and even potentially viable microorganisms between stellar systems. The timescales involved in interstellar transfer, measured in millions of years, exceed the known survival limits of terrestrial organisms under space conditions. Yet theoretical studies suggest that certain extremophile species might survive such journeys if protected within the interiors of cometary nuclei, where radiation exposure remains limited and temperatures remain stable. As 3 Atlas disappears into the cosmic darkness, now invisible to all but the most sensitive telescopes, and carrying within its ancient ice both the chemical memories of its birth around another star and the acquired signatures of its passage through our solar system, it continues a process of galactic chemical evolution that has operated since the first generation of stars began enriching interstellar space with heavy elements forged in their nuclear cores. In the infinite darkness beyond the outer planets, where the sun diminishes to little more than the brightest star in a field of distant lights, and the temperature of space approaches the cosmic microwave background that preserves the afterglow of creation itself. 3I Atlas continues its eternal journey with the patient persistence that characterizes all motion in the universe. The comet now travels at velocities that will carry it beyond the gravitational boundary of our solar system and back into the galactic medium from which it emerged, bearing within its nucleus both the pristine chemistry of its birth around another star and the accumulated memories of its passage through our own stellar domain. The trajectory that carries the comet toward its ultimate destination among the stars follows mathematical curves that extend across scales from the quantum fluctuations that govern atomic transitions to the large-scale structure of the galaxy itself. The same gravitational dynamics that determine the comet's hyperbolic orbit past Mars and through the inner solar system now guide its motion through the outer reaches of heliospheric space, where the solar wind gradually weakens and merges with the interstellar medium that fills the spaces between stars. These transition zones, neither fully solar nor truly interstellar, represent boundary regions where the physics of stellar influence gives way to the larger dynamics of galactic evolution and cosmic structure formation. The comet's nucleus, now stripped of its temporary atmosphere and reduced to its essential core of ancient ice and embedded dust, carries forward the accumulated thermal history of its encounter with solar radiation. The outer layers, modified by sublimation and thermal cycling during the active phase near Mars, preserve in their crystalline structure the record of phase transitions that occurred as materials formed around one star underwent processing by the energy output of another. This thermal memory, encoded in the molecular arrangement of water ice, and the distribution of trace chemical species throughout the nucleus, represents a form of information storage that operates on geological timescales and preserves data about stellar radiation environments across interstellar distances. The isotopic signatures within the comet's ice, now mixed through diffusion processes with small quantities of solar system materials incorporated during its passage through our planetary domain, create chemical fingerprints that encode information about 2 different epochs of stellar evolution and nucleosynthesis. The original isotope ratios, reflecting the nuclear processing that occurred in the core of the comet's parent star and the cosmic ray bombardment it experienced during its interstellar journey, now combine with trace signatures from our own solar nebula to create a chemical record that spans different regions of the galaxy and different generations of stellar death and rebirth. As 3I Atlas moves beyond the orbit of Neptune and enters the realm where Kuiper Belt objects mark the outer boundary of our solar system's planetary architecture, it passes through regions of space that contain the most primitive materials available for study within our stellar domain. These icy bodies, preserved in the deep freeze of the outer solar system since the epoch of planetary formation, represent compositional samples of the same stellar nebula from which Earth and the other planets condensed, yet they remained sufficiently distant from solar heating to preserve volatile compounds and organic materials that were lost from the inner planets during their formation and early evolution. The comparative chemistry between 3I Atlas and native Kuiper Belt objects provides insights into the differences between stellar systems that formed under different conditions of galactic chemical enrichment, stellar population characteristics, and interstellar medium composition. The comet's deficit in certain trace elements and its unusual isotopic ratios for common molecular species reflect the distinct stellar environment in which it formed, where different generations of stellar nucleosynthesis and supernova enrichment created chemical abundances that deviate from the solar system norm in ways that illuminate the diversity of planetary formation processes throughout the galaxy. Theoretical models of the comet's future trajectory, based on integration of its orbital motion through the gravitational field of the Milky Way galaxy, predict passages near other stellar systems over timescales that exceed the current age of complex life on Earth. These calculations, necessarily uncertain due to the chaotic nature of gravitational dynamics in systems involving multiple stellar masses and the unknown effects of encounters with interstellar clouds and dark matter concentrations, nonetheless suggest that 3I Atlas will eventually experience gravitational perturbations from other stars that could alter its trajectory in fundamental ways. The comet's journey through interstellar space will expose it to cosmic ray bombardment rates that vary with its position relative to supernova remnants, stellar wind boundaries, and the galactic magnetic field structure that deflects charged particles according to their energy and charge state. This variable radiation environment will gradually modify the nuclear composition of atoms within the comet's nucleus through spallation reactions that create new isotopic species and alter the chemical inventory that recorded conditions in the comet's birth stellar system. The accumulated effects of cosmic ray processing over millions of years will eventually erase some of the original chemical signatures, while creating new isotopic markers that record the integrated history of the comet's exposure to galactic cosmic rays. The possibility that 3I Atlas may eventually encounter another stellar system with its own planetary architecture raises questions about the role of such interstellar messengers in facilitating chemical and potentially biological exchange between different stellar environments. The timescales involved in such transfers, measured in millions to hundreds of millions of years, exceed the known survival limits of terrestrial organisms. Yet the comet's nucleus provides protection from radiation and temperature extremes that might allow certain classes of complex organic molecules to survive interstellar transport and contribute to the chemical inventory available for prebiotic evolution in other stellar systems. The statistical mechanics governing the motion of objects like 3I Atlas through the galactic gravitational field suggest that a small fraction of comets ejected from their birth stellar systems will eventually be captured by other stars, creating a slow but persistent process of material exchange that has operated throughout the history of stellar formation in the galaxy. This transfer mechanism, mediated by gravitational dynamics and operating over cosmological timescales, represents a form of chemical communication between stellar systems that could have profound implications for understanding the distribution of complex chemistry and potentially life throughout the galaxy. The comet's continued motion through space follows the same physical laws that govern the expansion of the universe, the formation of galactic structure, and the nuclear reactions that power stellar evolution. Its trajectory through the local group of stars carries it as a messenger between different epochs of cosmic chemical evolution, bearing materials that formed when the galaxy possessed different characteristics of star formation rate, metallicity, and large-scale structure than those observed in the current cosmological era. As 3I Atlas disappears beyond the range of human observation and enters the realm of purely theoretical prediction, it continues to embody the fundamental principles of physics that connect processes occurring on atomic scales to the evolution of cosmic structure over billions of years. The ancient ice within its nucleus preserves information about stellar nucleosynthesis, galactic chemical evolution, and the physical conditions that existed in interstellar space during epochs when the universe was younger and the local stellar environment possessed characteristics that no longer exist in our current galactic neighborhood. The infinite journey continues, carrying forward through space and time the accumulated memory of stellar death and birth, planetary formation and destruction, and the patient chemistry of cosmic evolution that operates on scales vast enough to encompass the formation of galaxies, yet precise enough to determine the nuclear composition of individual atoms forged in stellar cores and scattered into space by the deaths of massive stars, in the vast silence that follows cosmic encounters, where time itself seems to slow to the rhythm of galactic rotation and stellar birth. 3. Atlas continues its patient drift through the darkness between worlds. The mathematical precision that governed its trajectory through our solar system now guides it toward destinations that exist only in the theoretical frameworks of celestial mechanics. Points of light separated by distances that reduce even the speed of light to geological patience. The comet carries within its frozen heart the accumulated memory of two stellar systems, the ancient chemistry of its birth around a sun that died before our Earth learned to support complex life, and the trace signatures of our own solar domain, collected during its brief passage through the realm of planets and asteroids and cosmic dust that orbit in the gravitational embrace of the star we call our own. These chemical libraries, preserved in ice colder than the depths of terrestrial winter, will travel together through the galaxy long after our sun exhausts its nuclear fuel and joins the population of white dwarf stars that mark the endpoints of stellar evolution. The silence of interstellar space envelops the comet like a blanket woven from vacuum itself, broken only by the whisper of cosmic rays and the faint electromagnetic radiation that fills the universe with the afterglow of creation. Here, in the realm between stars, temperature and time merge into concepts that exist at the boundary between physics and philosophy, where the patient processes of atomic decay and nuclear transformation operate according to half-lives measured in billions of years. The ancient ice sleeps again, as it slept during the long journey that brought the comet from another stellar system to our own. The molecular motions that characterize matter at temperatures approaching absolute zero create a crystalline stillness that preserves chemical information with the fidelity of geological strata, each layer of frozen volatiles recording different epochs of the comet's formation and evolution. In this ultimate cold storage, the passage of millions of years becomes indistinguishable from the blink of an eye in the cosmic perspective that encompasses the birth and death of stars. Darkness reclaims the visitor as it moves beyond the reach of our sun's light, becoming once again a wanderer in the cosmic night that connects all stellar systems through the shared medium of space and time. The journey that brought it briefly into our gravitational family now carries it toward encounters with other suns, other planets, other opportunities for the patient exchange of materials that has operated throughout the history of the galaxy. The mathematics of orbital mechanics ensure that this departure, like all celestial motions, follows curves of perfect precision through space-time, yet the destination remains unknown, subject to the chaotic sensitivity that governs all dynamical systems involving multiple gravitational influences operating over cosmological timescales. The comet's future lies written in equations too complex for complete solution, yet too elegant in their underlying structure to exist without deeper meaning in the architecture of cosmic evolution. In the end, 3i Atlas becomes what it always was, a messenger between stars, carrying the accumulated chemistry of stellar nuclear synthesis across distances and timescales that reduce human history to the duration of a single breath. The ancient ice continues its eternal journey, patient as stone, persistent as gravity, carrying forward the memory of worlds we will never see toward destinations that exist beyond the reach of human imagination, yet remain connected to our own stellar neighborhood through the universal laws that govern the motion of matter through space and time. The cosmic dark embraces the traveler, and the infinite journey continues in silence vast enough to contain the dreams of gods.